Hi! In this presentation, I want to introduce you to a work resulting from the collaboration of University of Rome Tor Vergata, SACMAI Imola, Fusion for Energy, Università della Tuscia, and Ansys France. To prevent sudden and unexpected breaks that could lead to catastrophic failures and safety problems, it is required in several fields to study and predict the behavior of crack growth. A component undergoing cyclic loading may, indeed, experience the generation of crack that, generally, initiates on material surfaces in correspondence of singularities or stress concentrations. The evolution of numerical prediction tools and the increase of the computational power allows today to adopt well-consolidated and accurate finite element-based methodologies, able to predict the evolution of the flow by recurring to the concept of the stress intensity factor. An intrinsic characteristic of the FEM-based methods is, however, the requirement of a continuous remeshing to accommodate the numerical domain to a newly achieved crack geometry at each fatigue cycle. In this context, radial basis functions mesh morphing is emerging as a viable solution to replace the complex and time-consuming remeshing operation. The RBF-based mesh morphing tool can be indeed employed for the study of the crack growth, updating the flow front by automatically morphing the mesh, obtaining an evolutionary workflow suitable to be used for industriallysized grades. In this work, a review of the fracture mechanics application tackled by synergically employing a commercially available FEM solver, Ansys Mechanical, and an RBF Morph, will be shown. Among the interpolation methods available for engineering calculation, RBF are a very powerful tool, able to determine the values of a scalar function starting from a discrete set of points, named source points, in the native space or in any of its subspaces. The interpolating function is composed by a radial basis and by a polynomial. RBF can be defined in a generic n-dimensional space and depend on the distance that, in the case of morphing, can be assumed as the Euclidean norm of the distance between 2 points in space. If evaluated on the source points, the interpolating function gives exactly the input values. The solution of the RBF problem is associated to the solution of a linear system, the complexity of which depends non-linearly on the number of source points taken into account. Once solved the RBF problem, each displacement component can be interpolated by means of a linear system. Different RBF kernels can be chosen depending upon the wanted interpolation behavior. To evaluate the crack evolution, the displacement component can be imposed to the nodes of the crack front using mesh morphing. By exploiting the stress intensity factor, the Paris-Erdogan law can be used as shown in this slide. The effective stress intensity factor can be extracted for a given node from a finite element analysis, calculating the relative displacement at each iteration. The number of loading cycles related to such calculated value can be extracted employing the inverse formulas. Proposable flow was first implemented in Ansys Workbench for a simple circular notched bar, employing literature geometry. After a mesh convergence test with respect to the notch concentration factor, a first benchmarking was executed on a predefined set of crack geometries to test the reliability on the numerical results obtained by RBF mesh morphing, comparing them to a full remeshing. A three-dimensional model was realized using parabolic elements with the tetrahedrons and wedge elements around the crack front. The RBF setup employed to morph the baseline crack is shown in figure. Several runs were carried changing the crack aspect ratio under a tensile static load of 30 kN. To compare results to literature data, the curvilinear abscissa and the resulting stress intensity factors were normalized. The results, showing perfect agreement between morphed and remeshing cracks, are shown in the slide. Having demonstrated the ability of RBF morphing to adapt the crack shape to a new geometry, a crack growth simulation was carried, employing the Paris-Erdogan law with a 2 degrees of freedom model. The profile, approximated by a circular arc, was controlled by 3 points, A and C on the perimeter of the reduced cross-section, B on the symmetry axis. Results of crack propagation obtained for different numbers of cycles are shown in figure. Proposed method, refined for a three-dimensional problem, was also applied for the propagation study of a crack in a multi-degree of freedom case, evaluating its development from the free surface appearance to its complete evolution. An undersurface crack has indeed a circular conformation until the breakouts. Once reached the surface, the crack geometry assumes an omega-shaped that, during its evolution, transforms into a semi-elliptical configuration as shown in figure. This study aimed at two results. At first, that mesh morphing allows to reproduce the omega shape. At second, that the multi-degree of freedom model can be employed to demonstrate that the three-dimensional flow evolves from an omega shape to a semi-elliptical one during its development. The starting omega-shaped crack mesh was at first obtained by deforming by means of radial basis functions the mesh representing the semi-elliptical final configuration, in order to have a fair term of comparison in terms of geometries. The final flow evolved shape can be compared, after the study, with the one employed as a starting configuration before the initial morphing. The Ansys fracture tool was used to generate the semi-elliptical crack employed as a starting point. The RBF setup employed to obtain such a deformation consisted in controlling directly the crack front and by smoothly describing a similar deformation to the boundaries of the quarter node wedges wrapping the crack. Displacements were computed using the stress intensity factors and the Paris-Erdőn law for each node, applying them normally with respect to the crack front. Results in terms of crack shape and stress intensity factor are shown during crack evolution. To finally demonstrate its capability to tackle complex industrial applications, the method was applied to the evolution of two initial elliptical cracks in one of the port stub of the Iter vacuum vessel sector 5, and results have been compared to the ones obtained by the assessment performed in accordance to RCC-MR nuclear code. After first structural analysis, in which the most favorable location for the crack generation and evolution has been identified as the corner smoothed edge of the port stub, the propagation analysis has been carried out with the same setup both for the 2 degrees of freedom model assessment, foreseen by the nuclear codes, and the multi-degree of freedoms to compare results. The crack in the corner smoothed edge of the port stub was inserted by means of the Ansys fracture tool. The full load spectrum, such as gravity, normal operation conditions, major disruption, and magnet fast discharge, were taken into account by using the minor rule as detailed in the Iter vacuum vessel load specification manual. The evolution of the crack half width has been plotted against crack depth for the estimated life of 7,280 cycles. The comparison of the crack geometrical parameters demonstrates that the two models lead to very similar results. For geometrical reasons of the port stub, the fracture parameters curves are not symmetric with respect to the elliptical crack and minor axis. In this condition, the multi-degree of freedom model describes with a more accurate level of detail the asymmetric evolution of the crack, which leads to a higher growth of the crack side close to the smoothed edge, while the crack of the 2 degrees of freedom model remains elliptical during its evolution. A review of applications tackling numerical fracture mechanics obtained by exploiting FEA, Ansys Mechanical, and mesh morphing, RBF Morph, state-of-the-art tools was given. Two different approaches were presented in order to study the flow evolution by deforming the computational grid according to the Paris-Erdőn law using radial basis functions. At first, a 2 degree of freedom model guiding the in-plane crack development by using two stress intensity factors values, one on the in-depth point of the symmetry and one on the surface. Then a multi-degree of freedom model was put in place, evaluating the stress intensity factor along the crack profile, guiding its evolution by projecting the displacements along the crack normal. These two approaches were first demonstrated on notched bar and compared to literature data, then applied to the vacuum vessel port tube for the fusion nuclear reactor, Iter, demonstrating the ability of the proposed methods of tackling the evolution of a crack in a three-dimensional problem. Thank you for your attention.